Hi, today I'm going to discuss the solutions for the Atcoder Beginner Contest 419, problems A to E. For problem A, Takahashi is learning a language and he knows that red, blue, and green correspond respectively to SSS, FFF, and MMM. So we're given a string which is either red, blue, or green, and then we want to output the corresponding characters that the colors are matched with. And if the input is not one of these three colors, then we want to output the string unknown. So for this problem, we can directly check using an if-else statement to check whether the input is one of these three colors and match them with the corresponding output, and otherwise we output unknown. And let's directly look at the code. So here I used a if statement. I first inputted the string and then I checked the colors, whether it's red, blue, or green. And if it is, I output its SSS, FFF, or MMM. And otherwise I output unknown. Next, let's look at problem B. For problem B, we have an empty bag and we have Q queries. And we need to process each query in order. There are two types of queries. The type 1 is in the format 1x, where a ball with the integer x written on it is put into the bag. And for type 2, we need to output the minimum integer from all the balls in the bag. So we can solve this problem by using a priority queue. A priority queue is a data structure where when we push numbers into it, it will be sorted in either ascending or descending order. So depending on what we want. And in this case, we want the numbers to be sorted in ascending order. And each time we encounter a type 2 query, we would pop out the number in the front, which would be the minimum integer in the bag and be the answer that we want. And for more detail, let's look directly at the code to see how to implement this. So here I define my priority queue and I use greater int. This means that the numbers will be sorted in ascending order because the default for priority queue sorts numbers in descending order. And this part I'm processing the queries. For type 1 queries, I push them into the priority queue. And for type 2 queries, I print out the top number in the priority queue, which would be the minimum number. And I pop this out to ensure that the number doesn't get repeatedly used because we need to take out the ball, and so we're supposed to pop out the number. Next, we move on to problem C. For problem C, we have a grid with 10 to the power of 9 rows and 10 to the power of 9 columns. And for each, there are n people on the grid, and each of them are at the squares Ri and Ci. For each time, a person can move to an adjacent square on all 8 sides. So they could move to point I minus 1, j minus 1, I minus 1, j, and in all 8 directions. We want to find the minimum possible times when n people are all at the same square. we can solve this problem with binary search because we know that for any time under time t, the answer will not work. And for any time greater than time t, the people will be able to meet at a certain location and the answer would work. So this property allows us to use binary search on our answer time t. And because for each person, their initial location is defined by RICI, and they can move in all 8 adjacent points for each time t. So the resulting points after a certain time would mean that they would have an x position of Ri plus or minus time t and Ci plus or minus t. So for the binary search, we want to check whether this t allows all n people to meet together. And to do this, we want to find the minimum of all Ri plus t and Ci plus t. And this means that this value will be x max, and this value will be y max. This value will be x min, and this value will be y min. So we do this because Ri plus t is the maximum value that any person, the maximum x value that any person could have after time t. And we want to find the minimum of this because if we find the minimum of this, then this means that all people would be able to reach this value of x. And that's why we find the minimum. And we do so for y as well. We find the minimum to ensure that all people will at least be able to reach this maximum y value. And similarly, we do this for the x value Ri minus t. So this means that when we find the maximum, this means that all people will at least be able to reach this minimum value of x. And we do the same thing for y. And in the end, we can check if the maximum x value is greater than the minimum. So in the end, we can check if x max is greater than or equal to x min and whether y max is greater than or equal to y min. So if this is the case, this means that this time t would work, and this would return true and mean that our binary search would work. And so here is a visualization of what I mean. So this is a example input where 3 people are here. So they could each move in like all of these directions, like all 8 directions. And so this is the maximum x location that this person would be able to move to. And this is the minimum x location that this person will be able to move to. And we want to ensure that the maximum is greater than the minimum, or like greater than or equal to. So this means that they will be able to meet at some location. And this is the same thing for y, where we want to ensure that the minimum y is smaller than the maximum y. So this means that there's a region that all the people would be able to meet at. And next, we can look at the code. So I first inputted all the points and I stored them as pairs of integers. And afterwards, this part is the binary search. So I'm binary search on the time t. And the maximum time t would be 1 to the 10 to the power of 9 because that's the length of the grid. And here we do binary search, and possible is the function that I talked about to check whether a certain time t would allow the people to meet at some location. And here, this is the part that I mentioned. So we want to find, for all endpoints, we want to find a x min, x max, y min, y max for all of them. And to do so, we find the maximum of each point x minus t, and we do the same thing for all of them. And in the end, to check whether this certain time is possible, we check if the x min is smaller than or equal to x max, and y min is smaller than or equal to y max. And if this returns true, then this means that this time t is possible, and we could continue this with our binary search. And in the end, we would get L would be the minimum possible time. For problem D, we have n lowercase English strings. And so we have two strings, S and T, and we have operations that swap the characters L through R with like between S and T. So for example, for this operation, if L R is 3 to 5, then the characters CDF would be swapped with the characters IJK in between S and T. So S would become AB IJKF, and T would become GHCDEL. So this is one operation, and we want to find the string S after performing all M operations. However, we don't want to, because there's a lot of operations, so we don't want to swap them each time because this would exceed the time complexity. Then we want to use a method that will only swap the strings to their final position. And we know that so for example, if we swap these characters, like C, D, E, and I, J, K, then if another operation swaps these characters again, then they go back to their original value. So this gives us the idea to use prefix sum. We can use prefix sum to solve our problem because we can record how many times each character is swapped. And if it's an even number of times, then this means that we do not need to swap the characters. And if it's an odd number of times, then we would swap the characters when we print out the answer. So for example, for the test input case, we have S equals apple and T equals lemon. So if we use a prefix sum, then for the first operation 2, 4, then we could add 1 here and subtract 1 here. And we could add 1 here to match this operation and subtract 1 here. We could also add 1 here and then subtract 1 here for the last operation. And after we sum these values up, we will get a result of 1. So what this means is that these characters the characters from 2 to 5 are all swapped twice. So if they are swapped twice, then this means that they were swapped back to their original position. And since this character is swapped only once, then this means that we should swap the characters when we print out the answer. And in the end, when we print out S, we will get L P P L E because the first character is swapped. And now let's look at the code. So here, sum is the prefix sum array that I defined. And for each L and R, I add to the prefix sum at position L, and I subtract 1 to the prefix sum at position R minus 1, R plus 1, I mean, when, as I mentioned previously. And this part is we're computing the prefix sum. Then we loop through each character to check whether the prefix sum value is odd or even. If the value is odd, then this means that the character is swapped and we would print out this corresponding character from string T. Otherwise, we will print out the character from string S. And in this way, we don't actually have to swap the characters each time, and we only have to print out the characters. And in the end, when we know that whether each character should be swapped. Finally, we look at problem E. For this problem, we have a length n in integer sequence A from A1 to AN, and we want to add 1, increase some value of AI by 1 so that every length L contiguous subarray of A, the sum is a multiple of M. So this means that for every L numbers, every contiguous L numbers, when they sum together, the sum needs to be a multiple of M. And we want to find the minimum possible number of operations we need to have before we can achieve this goal. To do so, let's first look at how we can represent this condition. So the condition is that every L contiguous numbers need to sum to a multiple of M. And if we start with after L numbers, this needs to sum to a multiple of M, which can be represented like this. And in the next sequence of L numbers, they also need to sum to a multiple of M. And if we subtract this equation from this equation, then we get I plus L minus AI equals A equals 0 when modulo M. And this is because these values all cancel out. And then so what's left is this one and this one. And what this means is that AI plus L is equal to AI mod M. And this means that for there's a period where AI has the same remainder when divided by M with AI plus L. So there's different groups. And this means that our array can be separated into several groups like this. So AI and AI plus L, AI plus 2L, and so on will all be in the same group, and AI plus 1, AI plus 1 plus L these will all be again in the same group, and this goes on and on. So we will have multiple groups, and each one they will have the same remainder mod m. And then because of this, we can define a array called cost. And this would store the index I and the mod m value of j. And the index would be for this one, which defines which group that we're currently processing. And for the cost ij, this would represent the value we will have to increase ai plus l, ai plus 2l, which means that the value we will have to increase this current group to ensure that all values in this group have a mod m value of j. So all values in this group, which are ai plus l, ai plus 2l, will have the same remainder when divided by m, which is j, and cost ij will store the cost of ensuring that this group satisfies this constraint. And after we have this value for each group and each mod m value, we then have to make sure another condition, which is that for each L contiguous number, they need to sum to a multiple of m. And to ensure this, because now the numbers in A are all divided into several groups that have a period of L. So we only need to ensure that the first L numbers sum to a multiple of m. And to do this, we could use another DP. This time is the I still represents the index and J still represents the remainder. And we can find, again, this is the minimum cost, but now it's not in one group, but the first I groups to sum to a remainder of J mod M. So we want to find the minimum cost for the first I groups to sum to J mod M. And to look in detail at the DP transition, we would find for DP ij, it would be the minimum of, again, dp I minus 1 k plus cost. And here, let me explain. K would be a remainder for the previous index. So we would loop through this value, and the x would be the value that we need to make sure that afterwards the remainder is equal to j. So since we already know when we want to find the minimum over all k. So we loop through a value called k, which is the remainder for the first I minus 1 groups, and this is the group we want to transition from. And then we need to find the additional cost that is needed to make sure that afterwards the first I groups have a remainder of j. And so this value x would be determined by k and j, which we will look more into detail when we look at the code. And this ensures that Afterwards, after we add this cost, dpij has is the minimum cost for first I groups to sum to j mod m. And this part explains what I mean by different groups. So from what we know here, if we look at this example, the first number will be in the same group as the fifth number because L is 4 and this is a period. And also this number will be in the same group as this number. 9 will be in the same group as 2 and 1 will be in a group on its own. And next, we need to ensure that these groups all sum to a multiple of m, which we do by the dp. And now let's look at the code to talk about the details of the dp transition. And here's my code. Here I inputted all the values for a, and then this part I'm calculating the cost for each group, which is the definition I mentioned previously. So I would be the index, which is the index for each group, and j would be the remainder with modulo m. And for each number, j is the remainder, and I only need to loop through from 0 to L because there will only be this number of groups. And for each one, I add L to the index, and if the current value A is greater than J, then we need to add this amount, which is M minus AX plus J to the cost because we need to add to M and then add another J to make sure that the remainder will be J. And otherwise, we can just add J minus AX. And this processes the cost for each group and each mod M value. Then next, we process the DP. So for the first group, the DP definition is again for dpij, it represents the minimum cost for the first I groups to sum to a value of j mod m. And here is the DP transition that I mentioned previously. So again, this is similar to this part where we loop through k, and k is the remainder for the previous first I minus 1 groups. And x is the amount that we need to add by to ensure that the first I groups have a remainder of j. And this part is the same as this part, where if j is smaller than k, then we need to add m minus k plus j, and otherwise we can just add j minus k. And dpij finds the minimum cost from a transition of some value of k. In the end, our answer, we want to output dpl minus 1, 0, because we want to find the minimum value for the remainder to be 0. So this number has to be 0. And this is it for today. Thank you for listening.